In this video, we're going to go over section 8.3 and 8.4 from our textbook. So section 8.3, here I just have a bunch of, like a compilation of the different types of conic sections that we've looked at so far in sections 8.1 and 8.2. So far we've looked at conic sections that are of this form here, and these guys are parabolas, circles, ellipses, or hyperbolas. And so in section 8.3, the homework just wants you to be able to identify what type of conic section you're looking at based off of these characteristics here, and then be able to then rewrite the equation that's given to you in this form in the standard forms for these guys here. So the purpose of this video here is really to just compile the lecture notes that has all of the different types of conic sections here. So this table is super important and can easily help you identify what type you're looking at. And then I also have the steps for completing the square here, as well as the different forms for circles, parabolas, translated parabolas, ellipses, and hyperbolas here. So everything's kind of just compiled. You can find it all in one location on the lecture notes. So that's about it for section 8.3. We showed how to rewrite all of these guys in their standard forms in section 8.1 and 8.2. So go ahead and look back on those videos if you have any questions on doing so. All right, so this brings us to section 8.4 then. We're looking at parametric equations. So a plane curve is just going to be a set of points x comma y such that x is going to be equal to a function f of t and y is equal to some function g of t. So f and g are, like I said, both functions, and they're both going to be continuous on some interval. Now the equations x is equal to f of t and y is equal to g of t are what's called parametric equations with the parameter t. So both of these guys depend on what our t value is. Now parametric representations of a curve are not always unique. So one simple parametric representation for y is equal to some function of x is going to be given by this here. So we have y is equal to f of t, where x is equal to t. So let's look at an example of this where we don't have unique parametric representations of a curve. So we're given this equation here. What we want to do is find two different parametric representations for it, and this is the equation of the parabola. So for part A here, we want to let one parametric equation be x is equal to t. So for this one, it is just as simple as plugging in t for x into our equation. So we have y is equal to x plus 4 squared, but we're saying x is equal to t, so we just plug in a t there. And that's it for part A. Pretty simple. For part B, we want to let one of the parametric equations be x is equal to t minus 4. So again, we're just going to plug that value in for x. So we get this here. Now this one, we can simplify a little bit. We have t minus 4 plus 4 squared minus 9. So this ends up just being t squared minus 9. But that's it for that one. Now let's look at another example. We have the following plane curve given by these parametric equations here, and what we want to do is find a rectangular equation. Now, in order to find an equivalent rectangular equation given a set of parametric equations like this, what we want to do is eliminate the parameter t. So these guys are not dependent on t anymore. And the easiest way to do that is to rewrite t in terms of one of the other variables. Now looking at both of these parametric equations, it'll be easier to rewrite t in terms of x in this case. So that's exactly what we'll do here. X is equal to t to the 9th power. To get t alone, what we'll do is we'll take the 9th root on both sides of our equation. So we'll get that t is equal to the 9th root of x. And another nicer way to write this is x to the power 1 over 9. So now what we'll do then is we'll plug in this value for t. T is equal to x to the 1 over 9th power. So we'll just plug this in for t here, and we'll get a rectangular equation. So we'll get an equation that is just dependent on x, no longer on the parameter t. So what I mean is y is going to be equal to 9 ln of t, which is x to the 1 over 9 power. Now we can simplify this a little bit more using our exponential rule for logs. And so that rule says that if we have log of something to some power here, this power can come down in front of our, it's going to be the coefficient of our log function. So what I mean is this is equal to 1 over 9 times 9 ln of x. So that exponent goes away. Now these guys are going to cancel here, so actually what we end up with is y is equal to ln of x. So this would be our rectangular equation, and this would be the case for x being in between 0 and infinity. So t was in between 0 and infinity here, so that we'll have the same domain for our x variable here. And we can see that that's the case because this is going to be the domain for our natural log function as well. All right, let's look at another example. In this case, we want to graph the pair of parametric equations in the rectangular coordinate system. And we're given this pair here for t values in between 0 and 3 and including both of those. So in this case, what we'll do is we'll plug in our values for t. And so t is going to be in between 0 and 3. So we're going to include those values. What we'll do is just plug them into both of our equations and see what we get for x and y. So plugging t in for x here, we'll get 0 minus 2, so we'll get negative 2 here. Plugging 0 in for t for y is equal to 3t, we'll get 0. Similarly, setting t is equal to 1 here, we'll get negative 1 for the sky, 3 for the sky, and then so on. So we'll get 0 and 6, and 1 and 9 for t is equal to 3. So now what we can do is plot these points, and we're going to plot the point x comma y. We're looking at the rectangular coordinate system here. So our x value is going to be negative 2, our y value is 0, so at that point, our x value is negative 1, our y value is 3, and so on. So plotting these points and then connecting them, we'll get this line here. Alright, so the last thing we're going to look at is a projectile motion application here. So the path of a moving object with this position can be given by these functions here, where x and y are dependent on t, and t represents time. So these parametric equations give the position of the object at any time t. So looking at this example here, we're told that a projectile moves so that its position at time t is given by these parametric equations here. What we want to do is graph the path of the projectile and find the equivalent rectangular equation. So what we're going to do is input values for t and see what we get for x and y. So plugging these values in for t, we're going to get this for x and y. Now physically what this means here, I have this diagram here because we are going to graph the path of the projectile, but x is going to be our horizontal distance and y is going to be our vertical distance. Imagine throwing a football, you end up with a parabola shape and you are moving in the vertical and horizontal direction as the ball is being thrown. So what we can do is plot these points here. So at time t is equal to 0, so you haven't in this case shot the projectile yet. So we're going to have the point 0, 0 here. Then when our horizontal distance is approximately 110, our vertical distance is going to be 116. So maybe somewhere around there. Then when our vertical distance is 220, our horizontal distance is 104. So it's dropping a little bit, which makes sense with gravity. So maybe right about there. And then when our horizontal distance is 275, our vertical is going to be 50. So right about here. All right, so the path of the projectile kind of takes this path here before hitting the ground somewhere over there. Now, this makes sense. If you were to shoot a projectile, it would have this parabola shape. It would go high as long as it goes in this vertical direction as well, and then over time it's going to come back to the ground due to gravity. So this also tells us we could look at this equation here, and we can determine when the ball will hit the ground, what time it'll hit the ground, because we know that's going to happen when our vertical distance or our y value is equal to 0. So if we set this equal to 0 and factor this guy, we would actually get the time that the ball would hit the ground. So that would happen when our vertical distance is 0. At this point, we have no vertical distance, we have no height. All right, and then the last part of this question, we want to find the equivalent rectangular equation. So we know we can do that by eliminating our parameter t. Looking at our two parametric equations, it'll be easier to write t in terms of x here. All we have to do is divide by 55 on both sides. So we'll get that t is equal to x over 55. Now what we'll do here is we'll plug in that value for t into both of these guys here in our equation for y. So we'll get y is equal to 90 times x over 55 minus 16 times x over 55 squared. Now, while this is a correct answer, we can simplify this a little further, and be careful with that on the homework as well. So this is the same as and since this exponent here is being distributed to our x and our 55, in the bottom here we're actually going to get 55 squared, which will be this here. And then lastly, we can simplify these guys here. We'll divide the top and bottom by 5. We'll get 18x over 11 minus 16x squared over this here. And so this is our final rectangular equation fully simplified. Alright, so that'll be it for this video.